Hello everyone and welcome to this discussion on GIS analysis. This is part 2. Few more parts we will be having for this discussion. Because as said in the previous lecture that this is basically the heart or key part of GIS operations. So, after the build up of spatial GIS database, we try to do as much as analysis possible whatever the data which is available to us. And of course, as per our requirements, as per project requirements and as per the user given specifications. So, this kind of analysis. Now, in this part, the second part of GIS analysis, we are going to discuss this overlaying operations. So, the first two parts, data selection, query retrieval, we have already discussed, and reclassification in the previous discussion. Now, in this we will be focusing mainly on the overlaying operations, which are the basis of overlaying operations are set theory or Boolean logics. If you recall the Venn diagram, and that is what is the basis, but there things were much simpler. Like in these Boolean operators or in Boolean logic or these functions, we used to have A intersection B, like A union B, A exclusion B and A negation B. So, these when we were introduced the set theory in our 10+2 mathematics, then we are introduced to very simple kind of logical functions or this Venn diagram. But in GIS we can perform very complicated one, because we are not handling two layers having just single polygon each, but we might be having multiple layers and each layer might be having large number of polygons. But still the fundamentally it would remain same, that when we do A intersection V, then we are using this operator AND, or A union V, then we are using this OR. XOR, that means exclusion, and not included or negation we are using. So, these operators and in combination that means single we can use this operator, or multiple operators together we can perform analysis on our maps. And this logical functions or these overlaying operations can be performed not only on the vector data, but also on the raster data. So, in case of vector data mainly on polygons, but anyway you can also perform on polyline and points as well, but mainly it becomes little complicated in case of polygon theme. Whereas in raster no issue, because if all layers, all themes are georeferenced and they may be belonging to a common geographic area, then we can perform these Boolean operators. And so, for using there are multiple layers we can involve, and in combination we can also use vector and raster layer also together. So, we can perform these overlaying operations on all these. Basically overlaying operations, here one very simple example is given. On top we are having one map belonging to the same geographic extent, having two polygons A and B. And now for the same area we are having another layer polygon map which is having two different units 1 and 2. So, these polygons 1 and 2 are completely having different shape and size than polygon A and B of the top map. Now, when we intersect these two, this is what the output is coming, and now in output we are getting basically 4 polygons. So, why I am discussing this is that when in the real GIS operations, each map, each layer may have tens of polygons. So, if I am having say 10 polygon here and 10 polygon here, you may end up even with 100 polygons depending on the shape of polygons. So, now that map may become little complicated. So, if it becomes complicated and if it is possible to reclassify, like we took example in the previous discussion, of reclassification, then we can reclassify and reduce number of classes and merge some polygons only for our display purpose. So, in that way we can perform such analysis. Another example is here that one map, say A is having just 2 units and map B is having 4 units. Now, when we intersect with these two, this is what the result is. So, instead of 2 and 4, now we are having 6 units and new topology would be constructed, and that topology which will have extra tabular data or extra field in our attribute, like A1, A2 are coming here, and here B1, B2, B3 will come as a separate one. Similarly, in vector overlay operations, lot of possibilities are there. Like one possibility is about the impose, means basically it is intersecting. So, impose means map A is here, map B is here, output I am getting like this. And why I am showing these terms here, because in many softwares or in many literature, like a very famous book on GIS by Bonham and Carter, they have used these terms. So, many softwares may use these terms, but basic operations will remain only those 4, that intersect, union, not, and exclusion. So, that way basic operations are same, but maybe different terms are used. Now, here when we go for stamping, basically it is combining these two maps A and B and creating a union here. Similarly, a join, so this is also joining and merging few polygons here, like as you can see in this example in map C. Again compare A and B, when they are compared the common areas are selected, rest are excluded. So, this is exclusion possibility is there. Now, this clip or extract, it is also called extract in many GIS software like in ArcGIS, retrieving data based on basically a polygon boundary. So, here this is what is, if it in case of point data, this is example that I am having these polygons or circles, and these are my input coverage or point data. So, when I overlay these two, I get only selection of these 2 points. That means I am basically clipping or extracting only those points which are falling below these 2 circles, or like this point 2 and 3, point 2 and 3 are falling in within these 2 circles. Similarly, I might be having a line or polyline theme, and this is my input coverage where I am having many polylines, and the clip coverage is the same as in case of point theme. And then when I create this intersection, this is how, or I get this clip or extraction of polyline only for that circular region. Similarly, if I am having a polygon map, my input as a polygon map, there are just 3 units are there, and one is of course outside one. Then if I use the same clip coverage to extract, then I get something like this as shown here, that below for this circle I get this. So, all kinds of possibilities in case of vector data is like this. Similarly, a different term is used here is erase. So, basically it is excluding those areas which are common. So, this is my input coverage, this is erase coverage, and this is my output. So, whatever is falling with these circles is excluded in my output. Similarly, for polyline, if I use this erase coverage, that now the things which were, or polylines which were falling below these circles have been excluded. Same with my polygon coverage, my erase coverage is the same in these examples. Input coverage is a polygon having 4 units, 1, 2, 3, 4, and now it is excluded. So, the area below circles have been excluded or polygons have been excluded. So, we can have an extraction, that is intersection, exclusion, union. Union example is also there. It is combining all. This is my input map having two rectangular areas, another layer which is having hexagonals, and when I create a union I get everything together. In a more realistic one like input cover, union cover and output, something like that, I can have the, if I am having a sequence of themes is different, but output is going to be different. Here the red box, large box is first input coverage, union coverage is different, though output is like this. Similarly, if my input coverage is a small blue box or a square, red square is my union coverage, but output is going to be the same. So, this was the union example. In more, what would happen to our this union operator or operator, and or. So, and for intersection, this or operator, my attribute table will become richer and richer because it is getting information from second layer also. So, this is my union coverage, this is my input coverage where I am having 6 polygons, and when I create the union I am having now large number of polygons. In this particular example, now total number of polygons have become 15. And of course, input coverage will have a attribute field. Similarly, a union coverage will also carry its attribute field. So, originally these two input coverages, input coverage and union coverage has single attributes in this particular example. Now, in my output coverage, I am having now 2 fields. One attribute is coming from map 1 input coverage, another attribute is coming from my union coverage. So, likewise, I can have not only 2, but I can union many maps having different polygons together and can create one. The only problem is that whatever the output is coming, we should understand. We should be able to understand and utilize that one. Computer or mathematics point of view or from GIS operations point of view, all complicated these logical operations, nested operations are definitely possible. Another example of intersect is that when we use this Boolean or AND operator, that when 2 coverages are overlaid, only portion of the input coverage that falls inside the intersect coverage will remain in the output coverage, that we have seen these examples. Similarly, while intersect coverage must be a polygon, this is what the requirement or this clip part, that input coverage can be a line, polygon or point coverage. If you recall the discussion when we have been discussing about the point data, at that time I mentioned, but today again I will mention that sometimes we get a very big database, and I do not want that my system should be occupied with that database when my work involves only on a small area. For example, I may get all the villages data from 250,000 scale topo sheets on net. Now, through some portals on the internet. Now, I am focusing only in the villages of say Uttarakhand. So, why I should in my hard disk, why I should keep the entire database? So, what I would do, I will use a polygon, that means the intersect. For intersect coverage, I will use a polygon which will have the boundary of Uttarakhand, and I will do this overlaying operations, AND operator, and extract only villages belongs to the Uttarakhand. And what would happen that when I use on my point theme, when I use this political boundary of Uttarakhand, then output will have only those selected points in my theme, input theme, which belongs to the Uttarakhand geographically. Now, what I can do, I can save that selection as a separate file and can remove my entire database from my system. So, unnecessary I will not keep, because for a particular organization, suppose that organization is working for Uttarakhand, why to keep the villages data for entire India? You may have, if you are having liberty or a lot of space is available on your hard disk, you can keep as a separate. But in day to day operations, when I am focusing only say on Uttarakhand, why I should all the time display or bring the total file of entire India village, because there are thousands of villages, lakhs of villages. So why to keep that data? Similarly, for a drainage network, I may get some modeled drainage available on some portals for entire Asia. Now I am focusing mainly say on Ganga basin. So why I should keep in my hard disk the entire drainage network of entire Asia, which has been generated using digital elevation model through surface hydrologic modeling, and again using 30-meter resolution digital elevation model. That means it is a huge database, and unnecessary every time whenever I will display, it will display for entire Asia, but I am focusing mainly on say Ganga basin. So I want extraction of my data, clip the data or intersect the data only for Ganga basin. So what I need a polygon boundary of Ganga basin, which I will put over this and intersect, perform this AND operation through this Boolean logic and or map calculator, and I get only a drainage network for Ganga basin. So that way it helps in basically to generalize to reduce the data or reduce space on our hard disk. Unnecessary data should not reside, because unnecessary, if I keep displaying that data, it would take a lot of time, one, and in future that might be the reason of some errors in my GIS analysis, which will be based on such themes. So it is always very much required to extract your data, clip your data as per your requirements from a large database. Like here example is given that input coverage, this same example we have seen, this is polygon which is my intersected coverage, and instead of here circles I can have a boundary of Uttarakhand. I may have a soil map of entire India. I want to extract only for Uttarakhand like this. So I will get a output only soil map for Uttarakhand. So likewise I can create my own sub database which will be used later, and the speed of analysis speed will be also much higher rather than performing on entire database. Similarly, there is a identity selection is also there, with that everything located within the boundaries of input coverage is collected in the output coverage, and the boundary of the output coverage is identical to the input coverage. And what's like, for example, I am having this polygon scenario, identity coverage again those two circles. I am having input coverage like this, and when I do this also creates a output coverage like this. So identity procedure applies to the point, which you can apply to the point, line, polygon coverage. Even on the raster, no issue. So raster based operations, much more operations you can do on raster also. All arithmetic, these basic arithmetic operations, plus, minus, multiply and this subtraction, addition, and your multiplication and division, all four arithmetic basic arithmetic operations you can perform on raster layers. You can also perform relational functions, less than, greater than, equal to, or in combination also within the same syntax, within the same query. I can use different I can use some arithmetic, some relational or some logical operations together. So AND, XOR, or NOT, all these four basic logical operations I can use, and also conditional functions, if, then and else. These I also can use, and in combination. So in one single line query I can use all operators together, or from each category I can use individual operator. As I have been repeatedly saying, whatever the output which the system will create, only requirement is that we have to understand. That is the only thing which we require. So, like here I am taking example step by step, means from very simple example, then little complicated, and then we will go for more complications, and using initially only arithmetic operations, that means addition, subtraction, multiplication and division. So, here what I am saying to the system, that map C is going to be equal to map A plus 10. So, as you can see that these different cell values are having different values, and cell values like 5, when it is added with 10 it becomes 15. Similarly, 6 added with 10 becomes 16. Very simple arithmetic operation, what I have used only this plus 1. Similarly, I can add these map A and map B like this. So, my map C instruction is map C or map C1 is going to be map A plus map B. And as you can see that if I take this corner value for example, so 2 plus 8 becomes my 10. Very simple arithmetic operations can be done. Similarly, I can also do other operations like here. This is now example, so map C2 example. So, map A, now here in this one 3 operators are being used, rather all 4 operators are being used. Then minus map B divided by map A plus map B multiply by 100. So, all 4 operators have been used, and when my map C will carry that value. So, likewise you can do in one go, you can use all arithmetic operations in one go or other operations also. So, let us see some other examples also, like relational functions greater than, less than, equal to, or that one. Now, here the condition is the output maps, if map A is greater than the individual cell level, the operation will be done. So, if map A cell is more than map B, then it should fall as true, otherwise it is false. So, here what if I take this value, so this value is 5, map B value is 4, that means map A value is greater than map B, and therefore it is getting value 1. If I take this example, here the value 2 is less than 8, that means it is false and it is getting 0. Now, this output here in this particular example will become your binary output. So, from 2 colored maps you may end up with a binary, but if I require because I want operation something like this which is given in this example, I should be happy with that it is creating an output which is just based on the true and false conditions. So, this is relational function. Now, Boolean logic, another thing is we call as a truth table, and truth table means basically true and false. So, input and output table for Boolean operators, the 1 generally is the true value and the 0 is the false value. So, if like here the input attributes are like this for map A and B and likewise. So, if map A here is in A 1, in case of B is 1. So, if I perform this operator and that AND or intersection, that A and B, then it remains 1, not A, then it is false. So, this is in my truth table, it is false. A or B, anything that means 1, so it is true. A XOR B, it is false, 0. So, for all kinds of inputs, all scenarios are given when A and B are not 1 and 1. That means one is 1, another one is 0. Then A and B, of course it is false, not A is false, A or B, the one is there, so true is false, here is true and this is true. So, something like this we can create a truth table depending on our requirements, but these operations can be performed very easily using either query builder or map calculator. The most common one is the map calculator in ArcGIS. If we take the real example, like using this intersection statement here, that when land use equal to forest and slope equal to steep. So, two input maps are here, one is the land use map, another one is the slope map. An output map will satisfy these two conditions, that land use equal to forest and slope equal to steep. So, when these two conditions are there, all those areas will get a value, a true value, and rest are false where this is not getting, and where you may have the areas where you do not have any value either in one map or another, like here we did not have the value, therefore, the white areas are there or no data areas are there. So, in real examples similar operations, these Boolean logic operations can be done. Now, if I go for in combination of relational or logical operators, then similar outputs can be created depending on how many classes in each map are there. Like for example, in map A we are having 4 classes. Similarly, in map B again we are having here only 3 classes. So, the first condition is that the new output map D, where map A equal to forest and the operator is AND, intersection, and map B is less than 500. So, less than instead of less than 500. So, if these two conditions are being satisfied, then it would be true, otherwise it would be false. So, in these two conditions, so only if this wherever you are seeing 1 are getting satisfied, otherwise not. Similarly, for OR operator union, XOR, not, or this negation also it is possible. So, if these conditions are there, then they are satisfying, and the output we are getting, all 4 outputs, 4 examples of these Boolean relational or logical operators are in binary form, that is in true or false. There are a lot of such applications are there. When we are having very complicated maps and we want to create very simple maps which will tell very simply that what is there and what where these conditions are satisfying, where not, you can create such binary output maps. Now, conditional functions where if else conditions are coming. So, three things are possible. If false, then we will get the 0 value, again output might be the binary depending on the condition, and true 1, and unidentified will have a question mark or no data. So, here in map A we are having two, one is F, another one is having no value or no data, unidentified. In map B we are having just 3 classes which are the and all are forest, and that 700 meter, 600 meter, 400 meter, and different values are given. So, if I take this C example, map C example here, that if map A equal to forest, then 1, else unidentified, because I know while inputting I know that there are areas which do not have any other value, only along with this FF we are having value. So, my output map will have unidentified areas where things are like this, and otherwise everywhere it will be 1. So, F basically has got converted into 1 or a true value. Now, in another example, what the condition is that map C1 output, if for that output, if map A equal to forest, same condition as in case of the above example, However, one more operator has come, that is intersection and map B equal to 700. So, if these two conditions are getting satisfied, then true, otherwise false. Any one is not satisfying, it would be false. So, in map C1 output, what we are seeing, only this part, yellow colored part is falling as true, rest is going 0. Like for example, map A is forest. So, these areas are having definitely forest, and also map it is 7. 7 stands for 700. So, then these are satisfying to that condition. Rest are not satisfying, and therefore, in my this binary map only one will show the true, otherwise 0 or false. So, all kinds of operations in combination. Now, here I am using this intersection, here I am using a conditional operation, here I am using conditional as well as intersection in the second example. So, all combinations and permutations of these operators are possible through this analytical operations in this overlaying analysis. Now, here we also call that cross table or cross operations, where we can again create a cross map. Basically, it is through the table, and then using that attributes, the cross table attributes, we can reclassify our map as done in this case. So, again a map which is showing the land use of 3 types: forest and grassland and lake or water body. And another example is the geology, where only 2 types of lithology is present. One is the alluvium, another one is the shale. So, this one the geology one is much simpler than your land use, does not matter. Now, I can create a cross table. So, where forest and alluvium, 2 different maps, a value can be given 9. When forest and shale are there, then forest and shale, then value 8, and likewise I can assign values, and this cross map is basically having that information. So, that I can use to keep the information of both maps together in one map through my attribute table while crossing these 2 operators. And such operations we perform when we go for change detection analysis. For example, I am having a map, a land use map of 1990. For the same area, I am having a land use map of say 2000, and another land use map of the same area of 2010 and another 2020. That means I am having 4 maps having 10 years separation. Now, I can create a cross table that which land use has changed to which one in those 40 years or maybe last 10 years. So, if I take very simple one, that how in last 10 years which land use, whether the forest land has become open forest or grassland or wasteland. Similarly, a lake has become reclaimed land. Sometimes it happens the water bodies are reclaimed, and so through this cross table I can very easily understand that where the changes have occurred from which land use to another land use. So, that can be done through cross tables. So, this is very useful operations in real GIS projects, where a lot of such chain detections are also performed. Another example of cross table is here, that map A is input map, and where values are varying between 1 to 4. Here values are varying only between 5 to 6. Result map is something like this. And because for example, if I take this value here 8, so this is 5 added plus 3, it becomes 8. My cross table will have all information. So, likewise I can perform various kinds of overlaying operations depending of my requirements. I can use single operator Say within arithmetic I can use only the addition, or I can use all operators together, and in some very complicated analysis I can use all different types of operators in a different manner. So, few examples I have discussed with you. And so, with this we come to the end of this discussion about overlaying operations of GIS analysis part 2. Thank you very much.